My name is Dr. Muhammad Sirajo Abdullahi, a lecturer in the Department of Mathematics of Usman Danfodio University, Sokoto, in Nigeria. Today I will like to present to you an application of mathematics, in particular of topology, or why we need to study it. First, I will start with the math itself. Why do we need to study math? First is, when you study math, there are some kind of skills that you will build into yourself. One is the mathematical ideas or concept of knowing how to prove problems, the mathematical problems, how to solve mathematical problems. The second one is ability to not only solve basic problems, but complex problems that ones need to encounter in life. And also it will increase one's critical thinking ability, and also the reading comprehension, and also active learning. It will improve your active learning and understanding of many things. So on the ability part, you build a kind of mathematical abilities and also information arrangement or organization of information and deductive reasoning. So these are the general things that one's end when he studies, or when he or she studies mathematics. So what in my area of expertise is a bit of intersection of many areas, right? It's a bit of functional analysis, a bit of topology, and also a bit of algebra. But today I would like to talk about topology, which is an area in math that deals with like a generalization of the concept of nearness of objects as they relate in a space. That is why it is sometimes called rubber sheet geometry, because it allows one to play with object without changing, irrespective of the shape of that, or of the physical shape of that object. What I mean, for instance, is when you talk about geometry, when you look at the ball, okay, we are looking for concept that has to do with a solid ball, and when you maybe change the ball to another shape, like to square, then to geometers it's like a different object. But in topology it is a bit flexible rather than rigid as how the geometry is. Topology allows one to have objects to be deformed without either tearing, gluing, by only stretching. You can stretch object, like when you have for instance, one of the basic example that topologists used to give to people is saying that, okay, a cup of tea and also a donut, they are like similar spaces, they are like similar object. So to their mind, what they mean is, okay, it is flexible. What we can do is we can move from the cup of tea to the shape of donut without tearing the space, or without adding anything by gluing, by just simply stretching it. We mean it is flexible. We look at it as the cup is flexible, so we can change the handle. Will still remain as the handle, but the shape of the cup, we can change it to be the other part of the donut. And if it is a donut, you can simply hold some part and try to force the other part to look like the cup of the tea. And that's why it is flexible, and it is called rubber sheet geometry, because it allows that flexibility. And there are so many signatures, we call them topological signatures, or simply topological invariant, that most of the time we use either combinatorial approach to study them, because they are like things that remain after this process, which is called a kind of either homeomorphism or or a special case of that, which is called a homotopy, right? So that will, if two objects are homotopy, we kind of know that they share the same properties. So it is the properties we are interested in. Then we look at, okay, how we can check this kind of properties and try to between spaces, so that we can know, okay, if we have a space or an object that is difficult to study, but this object is similar in a topological sense to another object that is very common or easy to study, then we try to see how can we find an like a kind of process that tells us that they share similar properties. If they do that, then we, instead for us to study the complex one, then we can study the simpler one, so that we can whatever we need to know on the complex one, we can still look at it on the much easier one to study. So this is why topology is important, and it is applicable in many aspects, many places. One, it is applicable in dynamical system, in knot theory, and also in most recently in data analysis. We try to introduce some methods, topological methods of studying data and analyzing data by either classifying the data or clustering the data, or looking at some anomalies in the data, or looking at to have an idea of how can we visualize this data. Maybe from there we can know that, okay, this data is different from this and this is different from that, if they have different topological features. That's what we use. And what I forgot to say is topology originated from one renowned problem, which this is it French mathematician Bernard Euler. He tried to solve this kind of problem of relating to bridge. They call it Königsberg bridge problem, where we have, like, I think seven cities around an island, and there is only single bridges between any two city. But the problem is, it's just like a fantasy problem, which grow up to be like a kind of an important question, because it brings about the notion of graph theory and henceforth topological spaces. So the problem is, okay, how can I move from this city to another city by crossing the bridge only once and coming back to where I started? Then Euler found out that with the help of graph theory that this is not possible, and that is the very beginning of topology as it started, before the formal definition of topology we now have as union of something and what have you. So topology is very important because it gives us numerous aspects to see to how we can view things, because that flexibility it gives us, and the kind of topological invariant it produces is what are important in applications, right? Sometimes people use it in physics, in topological insulators. I think also computer scientists use it in defining networks. They have like topological networks in the arrangement of computer systems and computer networks. And also it is used in biological sciences, like I said, in data analysis. So people use it to visualize like cancer data and numerous kind of data, any biological related data. And also they use it in transportation, in solving transportation problems. Like maybe you have like a company that you want to know, okay, what is the optimal way I can share the resources I have among my clients. So you can use also topological methods to model your problem, so that you can, at the end of the day, you get an optimal solution, so that it will save you either time or it will save you cost. And not only that, it is also used in in other places like in the core mathematics. There are theorems that help us build a proof for some of the challenging problems we have, like the millennium problem. I know there is one on topology which was solved by one mathematician using dynamical system approach. So these are, I think, a few with the short time we have that I need to say about on topology, right?